95% of the universe is missing. Not misplaced, not unobserved in the way that distant galaxies are unobserved, present but simply too faint or too far to have appeared in our catalogs, missing in a more fundamental sense, present all around us, shaping every structure in the cosmos, pulling every galaxy into its orbit, and yet completely invisible, undetectable by any instrument that measures light, because dark matter and dark interact with light at all. They pass through matter like ghosts, leaving no trace except in the gravity they exert on everything around them. Everything you have ever seen, every star, every planet, every galaxy, every nebula, every photograph taken by the Hubble or Webb telescopes, everything that has ever been visible to human eyes or human instruments, accounts for roughly 5% of the total mass energy content of the universe. The other 95% is dark, in the most complete sense of that word. And in the first months of 2026, scientists are closer to understanding what that darkness is than at any point in the nearly 100 years since the mystery was first noticed. Welcome to Sleepy Science Stories. Tonight we are going into the invisible, into the part of the universe that makes up most of what exists, and that has been, for most of human history, completely beyond our ability to detect, measure, or understand. Dark matter is the most searched scientific mystery of this moment, the subject of active research on every continent, the target of detectors buried 2 kilometers underground, of space telescopes with unprecedented sensitivity, and of theoretical models that are being revised and challenged by new discoveries arriving faster than at any previous period in the history of cosmology. The story of dark matter is the story of science learning to study something it cannot see, to map something it cannot touch, and to understand something that refuses to announce its presence in any way except by the gravitational effect it has on everything else. It is a story about inference, about patience, about instruments pushed to their physical limits, and about a mystery so large that solving it would require rewriting the most fundamental theories of what the universe is made of. The story of dark matter is the story of science learning to study something it cannot see, to map something it cannot touch, and to understand something that refuses to announce its presence in any way except by the gravitational effect it has on everything else. It is a story about inference, about patience, about instruments pushed to their physical limits, and about a mystery so large that solving it would require rewriting the most fundamental theories of what the universe is made of. Tonight we follow that story from its origins to its present frontier, through the underground detectors listening for collisions that may never come, through the space telescopes mapping the invisible skeleton of the cosmos, through the gamma-ray signals that may be the first glimpse of what we have been searching for, and through the theoretical debates that are reshaping our understanding of what the universe's hidden majority might actually be. The dark matter problem is the universe's way of telling us that we have, so far, understood only a small fraction of what exists. The rest is dark, and patient, and waiting to be found. Tonight we will follow the full arc of that story, from Fritz Zwicky's observation of galaxies moving too fast in 1933, through the decades of null results in underground laboratories, through the stunning new dark matter map produced by the James Webb Space Telescope in January 26, and through the gamma-ray signals and neutrino interactions and quantum fuzzy particles that are reshaping the search in 2026. This is the most active moment in the history of dark matter research, and there has never been a better time to understand what is at stake. Let your breathing slow. Let the room settle around you. Tonight we explore the 95%. The dark matter problem began with a speed that was too fast. In 1933, a Swiss astronomer named Fritz Zwicky was studying the Coma Cluster, a large collection of roughly 1,000 galaxies bound together by gravity, located about 320 million light-years from Earth. Zwicky was measuring the velocities of individual galaxies within the cluster, and what he found did not match what gravity, as then understood, predicted it should be. The galaxies in the Coma Cluster were moving far too fast. Specifically, The outer galaxies of the cluster were moving at velocities so high that if the only gravitational pull holding the cluster together were the visible matter, the galaxies should have flown apart long ago. The cluster should not exist as a bound structure. And yet it did, and had for billions of years. Zwicky calculated the mass needed to hold the cluster together gravitationally, given the measured velocities, and found that it was about 400 times the mass of all the visible galaxies combined. Something was providing an enormous additional gravitational pull that the telescopes could not see. He called it Dunkel Materie, dark matter, and his conclusion was dismissed by most of his contemporaries as an error, an artifact of primitive measurement methods, or an overstatement of a minor anomaly. He was not wrong. The evidence for dark matter accumulated slowly through the following decades, from multiple independent directions, and by the 1980s it had become one of the most robustly supported conclusions in astrophysics. Galaxy rotation curves provided the clearest confirmation. In every spiral galaxy studied, stars in the outer regions rotated around the galactic center at speeds far higher than the visible mass could support, implying an invisible halo of mass extending well beyond the visible disk. The evidence from gravitational lensing was equally compelling. General relativity predicts that mass bends the path of light passing near it, and the degree of bending in light from distant galaxies, as measured by multiple independent research groups, consistently required much more mass than the visible matter could account for. In the most dramatic cases, like the bullet cluster, the distribution of dark matter inferred from lensing was directly visible as a separate component from the visible gas, providing what many researchers consider the most direct evidence for dark matter ever obtained. What dark matter is, and where it comes from, remained unknown despite the robust evidence that it exists. That question has driven one of the largest coordinated scientific efforts in history, involving hundreds of research groups, billions of dollars in detector construction, and decades of theoretical development. And it remains, as of today, the deepest open question in fundamental physics. It is worth pausing on what it means that the evidence for dark matter comes from so many independent directions. The galaxy rotation curves that motivated researchers in the 1970s to take the problem seriously are one line of evidence. Gravitational lensing is a second, completely independent line. The temperature and distribution of hot gas in galaxy clusters is a third. The statistical properties of the cosmic microwave background are a fourth. The formation and distribution of large-scale structure in the universe is a fifth. Every one of these different measurement techniques, using different instruments, different astrophysical systems, and different physical effects, points to the same conclusion. There is far more mass in the universe than can be seen, a mystery that explains itself consistently across so many independent observations is not an artifact of measurement error. It is real, and it is waiting to be understood. Understanding what dark matter is requires understanding the long list of things it has been ruled out to be, because the history of dark matter research is substantially a history of eliminating candidates and narrowing the range of possibilities. The first serious dark matter candidates were ordinary matter that simply could not be seen. Objects like brown dwarf stars too small to ignite nuclear fusion, and therefore invisible, or black holes formed from normal matter, or large clouds of cold hydrogen that emit no light. These candidates are called MACSHOs, for massive astrophysive compact halo objects, and searches using gravitational microlensing, in which the temporary brightening of a background star indicates that a massive dark object has passed between it and Earth, were conducted over decades and found that MACOs could account for at most a small fraction of the dark matter. More fundamentally, the total amount of ordinary matter in the universe is constrained by nucleosynthesis, the production of light elements in the early universe. The proportions of hydrogen, helium, lithium, and other light elements produced in the first few minutes after the Big Bang depend sensitively on the density of ordinary matter, and observations of those proportions place a firm limit on how much ordinary matter, whether visible or dark. That limit is well below the total dark matter density inferred from gravitational observations. Dark matter cannot be ordinary matter. It must be something different in kind, not just in visibility. The leading theoretical candidate for decades was a class of hypothetical particles called WIMPs, for weakly interacting massive particles. WIMPs are predicted by extensions of the standard model of particle physics, particularly by supersymmetry, a theoretical framework that doubles the number of fundamental particles by proposing a heavier partner for each known particle. WIMPs would interact with ordinary matter through the weak nuclear force, which means they would be detectable in principle by incredibly sensitive underground detectors that could record the rare collision between a WIMP and an atomic nucleus. Underground detectors are shielded from the cosmic ray background by kilometers of rock, because cosmic ray secondary particles would overwhelm any WIMP signal at the surface. The world's most sensitive WIMP detectors, including Pandax in China, Lux Zeppelin in the United States, and Xenon in Italy, have operated for years and recorded billions of background events in search of the distinctive signal that a WIMP collision would produce. None of them has found convincing evidence of a WIMP. The null result from decades of WIMP searches has not disproven the existence of WIMPs, because the detectors have limits of sensitivity and WIMPs could exist at masses or interaction strengths outside the search range. But it has substantially shifted scientific attention toward alternative candidates, and the dark matter landscape in 2026 is richer and more diverse than it was when WIMPs were the dominant framework. The question of what dark matter is has, in recent years, become more open rather than more resolved, even as the evidence for its existence has grown stronger. The failure to find WIMPs after 3 decades of searching is itself a significant scientific result. It has taught us that if WIMPs exist, they are either lighter, heavier, or more weakly interacting than the simplest supersymmetric models predicted, and it has pushed the field toward a broader and more creative exploration of the dark matter candidate space. In science, a definitive negative result is not failure but progress, the elimination of a possibility that clarifies the remaining options and focuses effort on the territory that has not yet been explored. The WIMP null results have been among the most productive negative results in modern physics, reshaping the entire theoretical and experimental program of dark matter research. With WIMPs failing to materialize in the detectors designed to find them, the theoretical landscape of dark matter candidates has expanded dramatically, and the searches being conducted today cover a range of possible particles and properties that would have seemed extravagantly speculative a generation ago. Axions are one of the most compelling current candidates, originally proposed in the 1970s to solve an unrelated problem in quantum chromodynamics called the strong CP problem. Axions are predicted to be extraordinarily light particles that interact extremely weakly with ordinary matter and with light. If they exist, they should be produced in enormous numbers in the early universe and form a diffuse, nearly invisible background of particles that could account for the observed dark matter density. Several experiments are currently searching for axions by looking for their predicted conversion into photons in the presence of strong magnetic fields. But the search is technically demanding because the conversion probability is extremely low. Sterile neutrinos are another candidate, hypothetical particles related to the known neutrinos but even more weakly interacting. They would have been produced in the early universe and could account for the observed dark matter density without violating any current experimental constraints. Searches for sterile neutrinos look for the X-ray photon that they are predicted to emit when they decay, and a tentative signal at 3.5 kiloelectron volts was reported in X-ray observations of galaxy clusters in 2014, though the interpretation of that signal remains controversial and subsequent analyses have found conflicting results. Primordial black holes, formed not from the collapse of massive stars but from density fluctuations in the very early universe, have experienced a revival of interest as dark matter candidates. The detection of gravitational waves from black hole mergers by LIGO has raised the possibility that some of those mergers involve primordial black holes rather than stellar origin black holes, and if so, they could constitute a significant fraction of the dark matter. The allowed mass range for primordial black holes as dark matter has been substantially narrowed by multiple observational constraints, but a window of allowed masses around the range of asteroids to the Moon remains open. Fuzzy dark matter, also called ultralight dark matter, is a candidate that has attracted increasing theoretical interest because of its potential to resolve discrepancies between the predictions of cold dark matter models and observations of the distribution of small galaxies. In fuzzy dark matter, the dark matter particle is extraordinarily light, with a mass of perhaps 10 to the negative 22 electron volts, so light that its quantum wavelength is astronomically large. This quantum fuzziness would suppress structure formation on small scales, potentially explaining why we observe fewer small satellite galaxies than standard cold dark matter predicts. Research published in early 2026 found evidence, from gravitational lensing of distant quasars, that the universe's dark matter may indeed be fuzzier and more quantum-like than the cold dark matter paradigm assumes. The breadth of this candidate landscape reflects both the depth of the mystery and the ingenuity of the scientists pursuing it. Every candidate has motivated new experimental searches, new theoretical developments, and new observational programs, and the field of dark matter research has never been more active or more inventive than it is right now. The diversity of candidates also reflects something important about the nature of the problem. When a scientific mystery resists solution for nearly a century, it is often because the solution requires ideas that were not available when the mystery was first posed. The dark matter problem was first identified with the tools of 1930s astronomy, when the only detectable particles were those of ordinary matter, and the theoretical framework did not include any of the exotic candidates that are now considered most promising. The candidates being seriously explored today, actions, sterile neutrinos, primordial black holes, fuzzy dark matter particles, and others, emerged from theoretical developments in particle physics and cosmology that had nothing to do with the dark matter problem originally, and were recognized as dark matter candidates only later. The solution to the dark matter problem may require ideas that have not yet been developed, and that is precisely why the current period, with its expanding experimental reach and its rapidly evolving theoretical landscape, is so productive. On January 26, 2026, NASA published one of the most detailed maps of dark matter ever produced, created using data from the James Webb Space Telescope. The map covers a region of sky called the Cosmos Field, containing nearly 800,000 galaxies, and it shows the distribution of dark matter as a blue overlay on the galaxy distribution, inferred from the gravitational lensing effects that the dark matter produces on the light from those galaxies. Where visible galaxies cluster, the dark matter clusters too. Where thin strings of galaxies connect larger clusters, thin strings of dark matter run alongside them. The correlation between dark matter and visible matter is, as one of the researchers on the project noted, so tight that it cannot be a coincidence but must reflect dark matter's gravity, pulling ordinary matter toward it throughout the 13.8 billion years of cosmic history. The Webb map improves on the previous best dark matter map, produced by the Hubble Space Telescope in 2007, in resolution and depth. Webb's infrared sensitivity allows it to detect galaxies at greater distances, and with greater precision than Hubble, enabling gravitational lensing measurements that are more accurate and that cover a larger effective volume of the universe. The result is a dark matter map that shows structure at smaller scales, confirming and extending the picture of the cosmic web that earlier surveys had begun to sketch. The map has several scientific implications beyond its visual impact. The statistical properties of the dark matter distribution, measured from the lensing signal, provide information about the fundamental parameters of cosmology, including the density of dark matter, the rate of structure growth, and the properties of dark energy. One of the tensions in current cosmology called the S8 tension, involves a discrepancy between the clumpiness of the universe predicted by the cosmic microwave background observations and the clumpiness measured by large-scale structure surveys. The Webb lensing data bears on this tension, and its analysis contributes to the ongoing effort to understand whether the standard cosmological model is complete or whether it requires modification. The upcoming Nancy Grace Roman Space Telescope, scheduled to launch in autumn of 2026, will extend the dark matter mapping program to an area 4,400 times larger than the cosmos field, providing a statistical sample of dark matter distribution that dwarfs anything currently available. Roman's primary scientific goals explicitly include measuring dark matter's fundamental properties and tracking how those properties may have changed over cosmic history. The combination of Webb's depth and Roman's breadth will, over the next decade, transform our understanding of the dark matter distribution in the universe from the maps we have today into something far more complete and far more revealing. The visual power of the Webb dark matter map, showing 800,000 galaxies overlaid with the blue ghost of an invisible structure that outweighs all of them combined, is difficult to overstate. It is a map of something that was not known to exist 100 years ago, produced by instruments that are among the most sophisticated machines humanity has ever built, and it shows, in blue and white on a field of black, the skeleton of the universe. The dark matter map also carries a message about methodology that deserves recognition. The researchers who produced it did not detect dark matter directly. They inferred its presence from the distortions it produced in the light from 800,000 galaxies, using the mathematics of gravitational lensing to reconstruct the mass distribution from the pattern of distortions. The technique is indirect in the way that all the best dark matter science is indirect, working through the effects rather than the cause, building up a picture of the invisible from the catalog of what can be seen. And the fact that a technique so reliant on inference and statistical analysis can produce a map of this clarity and detail is itself a testament to how far both the observational and the analytical tools of cosmology have advanced since Wiki first noticed that the Coma Cluster's galaxies were moving too fast. While the space telescopes map dark matter's large-scale distribution, a parallel effort underground is attempting to detect individual dark matter particles directly, one collision at a time. The principle of direct detection is straightforward. If dark matter particles exist and pass through ordinary matter, which the gravitational evidence strongly implies they do, then occasionally one of them should collide with an atomic nucleus in a sensitive detector. The collision would be rare, perhaps occurring once in years or decades in a kilogram of detector material, and the energy deposited would be tiny, far smaller than any ordinary radioactive decay or cosmic ray interaction. But with sufficiently sensitive detectors, shielded from all other sources of background radiation, the signal might be distinguished from the noise. The shielding requirement is the reason these detectors are underground. Cosmic ray secondary particles, particularly muons, can mimic the signal from dark matter collisions if they penetrate the detector. And at the surface, the muon flux is too high to suppress sufficiently. By going deep underground, under kilometers of rock, the muon flux is reduced by factors of millions, making it possible to build detectors sensitive enough to search for the incredibly rare signals from dark matter. The most dramatic news in direct detection in early 2026 came from the SuperCDMS experiment at SNOLAB, located 2 kilometers underground in a mine in Sudbury, Canada. On March 17th of this year, the collaboration announced that the experiment had reached its operating temperature, just above absolute zero, enabling its superconducting sensors to function for the first time at full sensitivity. The ultra-cold environment minimizes thermal noise to levels that allow detection of the tiny energy deposits from low-mass dark matter particles, extending the search into a mass range that previous experiments could not access. SuperCDMS is designed to search for dark matter particles much lighter than WIMPs, in the range of masses where the quantum effects of fuzzy dark matter become relevant, and its first science results are anticipated within the coming year. The Luxaplin detector, located more than 1.5 kilometers underground in the Homestake mine in South Dakota, uses 10 tons of liquid xenon as its detection medium and is currently the world's most sensitive WIMP detector, having set the most stringent limits on WIMP-nucleon interactions over most of the WIMP mass range. Its data continues to be analyzed, and any signal above its background would represent one of the most significant discoveries in the history of physics. A new approach to direct detection has been opened by the confirmation, in January 2026, of the Migdal effect, a phenomenon predicted in 1939 by Soviet physicist Arkady Migdal. When an atomic nucleus recoils after being struck by a particle, the rapid change in the atom's electric field can eject one of the nucleus's orbiting electrons. This ejected electron produces a detectable signal that is in addition to the nuclear recoil signal, effectively amplifying the detectable response to a dark matter collision. The confirmation of the Migdal effect by a Chinese research team, published in Nature, opens a new pathway for detecting light dark matter particles that would otherwise produce nuclear recoils too faint for current instruments to register. The direct detection program has, so far, produced limits rather than discoveries, establishing that dark matter does not have the properties required to produce detectable signals in the experiments conducted to date. Each null result narrows the space of allowed dark matter models and pushes theorists toward candidates that interact more weakly or at different mass scales. The narrowing is progress, even without a detection. In November 2025, a researcher at the University of Tokyo published an analysis of data from NASA's Fermi Gamma Ray Space Telescope that attracted immediate and intense attention in the astrophysics community. Tomonori Totani detected a halo of high-energy gamma rays surrounding the center of the Milky Way that closely matched the spatial profile predicted by dark matter annihilation models. When two dark matter particles collide and annihilate each other, the standard theoretical framework predicts that the collision should produce gamma rays at a specific energy and with a specific spatial distribution, peak toward the galactic center where dark matter density is highest and falling off in a predictable way with distance from the center. Totani's analysis found precisely this pattern in the Fermi data at energies around 20 gigaelectron volts. The galactic center gamma ray excess, as the anomaly is known, has been detected and debated before, first reported in 2014 and argued over since. The difficulty is that the galactic center is an extraordinarily complex region filled with many sources of gamma rays, including pulsars, supernova remnants, and diffuse interstellar processes, and separating a dark matter signal from this crowded background requires precise modeling of all the other emission components. Different groups using different models of the background have reached different conclusions about whether the excess is real, whether it is explained by conventional astrophysical sources, and whether its properties are consistent with dark matter or not. Totani's 2025 analysis argued that the signal he detected could not be easily matched to any known conventional source or combination of sources. The spatial profile was consistent with dark matter annihilation to a degree that, in his assessment, merited serious consideration as the first observational evidence of dark matter. The energy of the signal matched the range predicted for dark matter particles at accessible masses. The caveat that Totani himself emphasized is that independent confirmation is essential. One researcher's analysis, however careful, does not constitute a discovery. Other teams need to analyze the same data with different methods, different background models, and different assumptions, and if they find the same signal, the case becomes substantially stronger. If they find that the signal disappears under different but equally reasonable assumptions, the case weakens. This process of independent verification is exactly what the astrophysics community is now undertaking, motivated by the significance of what a confirmed dark matter detection would mean. If the galactic center excess is confirmed as a dark matter signal, it would represent the first time in human history that a form of matter making up approximately 27% of the total mass energy of the universe has been directly observed. The significance of that moment, for physics, for cosmology, and for our understanding of what the universe is made of, is difficult to overstate. It would not answer all the questions about dark matter, because knowing that dark matter exists and knowing what it is are different things. But it would establish that dark matter has properties accessible to existing instruments, and it would provide a concrete target for the next generation of experiments to characterize. The search for the dark matter annihilation signal at the galactic center is being pursued by multiple independent teams using different analysis methods and different datasets, and the convergence or divergence of their results over the next several years will be one of the most closely watched developments in astrophysics. The Fermi telescope continues to accumulate data, and the statistical power of its observations increases with every year of additional operation. Complementary searches using the Cherenkov Telescope Array, a new ground-based gamma-ray observatory, will extend the galactic center observations to higher energies and with improved angular resolution, potentially providing the independent confirmation that a tentative detection requires before it can be called a discovery. One of the most surprising developments in dark matter research in early 2026 has been the evidence, published in Nature Astronomy in January of that year, that dark matter and neutrinos may interact with each other. Neutrinos are the ghostliest particles in the Standard Model, nearly massless particles that interact only through the weak nuclear force and gravity, and that pass through ordinary matter almost without interaction. Billions of neutrinos produced in the Sun pass through your body every second without leaving any trace. They are the least detectable particles that physics currently recognizes, which makes the possibility that they interact with dark matter, which is itself famously undetectable, particularly unexpected. The evidence for neutrino-dark matter interaction comes from a tension in the standard cosmological model called the S8 tension. The S8 parameter measures the clumpiness of the universe, how much ordinary matter and dark matter cluster together on large scales, and it can be measured in two independent ways. One measurement comes from the cosmic microwave background, the afterglow of the early universe, which imprints information about the universe's composition at the time of last scattering onto the pattern of tiny temperature fluctuations that permeate the sky. The other comes from surveys of the large-scale structure of the universe today, measuring how galaxies cluster on scales of hundreds of millions of light years. The problem is that these two measurements disagree. The universe today is less clumpy than the cosmic microwave background data predicts it should be. This discrepancy, the S8 tension, has resisted explanation by any modification to the Standard Model's accounting of ordinary matter or dark energy. But a team led by Sebastian Trojanowski at the National Center for Nuclear Research in Poland found that if dark matter and neutrinos interact even slightly, transferring a small amount of momentum between them during the universe's early development, the resulting suppression of small-scale structure growth would reduce the clumpiness of the universe in exactly the way the tension requires. The interaction they propose is new physics, not present in the Standard Model, but it is not arbitrary. It is a specific, testable modification with implications beyond the S8 tension, implications for the distribution of dark matter in galaxy halos, for the spectrum of the cosmic microwave background, and for the properties of future large-scale structure surveys. The Vera Rubin Observatory, which began full operations in 2025 and is surveying billions of galaxies in the southern sky, and the Euclid satellite, launched in 2023, are expected to produce data that will substantially confirm or refute the neutrino-dark matter interaction hypothesis within the next few years. If confirmed, the interaction between dark matter and neutrinos would represent a fundamental extension of physics beyond the Standard Model, connecting the dark sector to the known particle physics in a way that no current theory predicts. It would mean that dark matter is not as completely isolated from the rest of physics as the null results of WIMP searches have suggested. It would open new experimental avenues for studying dark matter properties. and it would bring the universe's hidden majority one step closer to being understood. The neutrino-dark matter interaction story is also a reminder that dark matter may be part of a larger dark sector, a collection of particles and forces that interact with each other, but only weakly or not at all with ordinary matter. If such a dark sector exists, it might have its own dynamics, its own mediator particles analogous to the photon or W and Z bosons of the Standard Model, and its own characteristic signatures in astrophysical observations. The search for evidence of a dark sector is one of the expanding frontiers of both particle physics and cosmology. And the hint of neutrino-dark matter interaction is one of the more intriguing pieces of data pointing in that direction. Whether it survives further scrutiny and accumulating data is the question that the next generation of surveys will begin to answer. One of the longest-standing tensions in dark matter research is the discrepancy between the predictions of the cold dark matter model and the observed properties of small galaxies. And understanding this tension illuminates both the successes and the limitations of our current picture of dark matter. The cold dark matter model, abbreviated as CDM, is the foundation of modern cosmology's account of structure formation. In this model, dark matter consists of particles that were moving slowly at the time of their formation in the early universe, and these slow-moving particles clump easily under gravity, forming dark matter halos that become the seeds of galaxies and galaxy clusters. The model successfully accounts for the large-scale distribution of galaxies, the statistical properties of the cosmic microwave background, and the general features of the cosmic web, with a precision that has been confirmed by multiple independent observations. But at smaller scales, the cold dark matter model makes predictions that do not match observations as cleanly. The model predicts many more small satellite galaxies around a galaxy like the Milky Way than are actually observed, a discrepancy called the missing satellites problem. It predicts that the cores of dark matter halos should have a sharp central density peak, called a cusp, but observations of dwarf galaxies suggest that their dark matter halos have cores with roughly constant density rather than cusps, and it predicts the existence of a number of large, dense substructures within galactic halos that have not been found. These small-scale tensions have been debated for decades, and several explanations have been proposed. One class of explanations invokes the effects of ordinary matter, specifically the feedback from star formation and supernovae, that can redistribute dark matter within halos, potentially turning cusps into cores and destroying small satellites. These baryonic feedback models have become increasingly sophisticated, and modern simulations suggest that many of the small-scale discrepancies can be resolved without modifying the dark matter model itself. But another class of explanations proposes that cold dark matter is not quite right, that the dark matter particles have some property, such as self-interaction, quantum fuzziness, or a small interaction with normal matter, that modifies the structure of halos at small scales without disrupting the successful large-scale predictions. These alternative dark matter models have become increasingly specific and testable, and the observations being produced by new surveys and simulations are increasingly able to distinguish between them. Research published in early 2026 using gravitational lensing of distant quasars found evidence for what the authors described as fuzzy or quantum dark matter, a form of dark matter with quantum properties at astronomical scales. The gravitational lensing measurements showed patterns of distortion in the light from background quasars that were more consistent with a dark matter distribution that was smoother at small scales than cold dark matter predicts, suggesting that the invisible scaffolding of the universe has a quantum granularity that modifies its behavior at the level of individual galaxies and their surrounding halos. This is not a definitive result, and the cold dark matter model has not been ruled out, but it is precisely the kind of observational constraint that the field has been working toward for decades, and it represents the increasing precision with which the dark matter problem is being approached from multiple directions simultaneously. The structure problem is ultimately a problem about whether dark matter behaves exactly as a pressureless, collisionless fluid of particles with no interactions beyond gravity, or whether it has additional properties that modify its behavior at small scales. The observational data is providing increasingly precise tests of both possibilities, and the tension between cold dark matter predictions and small-scale observations is one of the strongest empirical motivations for exploring alternatives. The coming decade of large-scale surveys, simulations, and direct measurements of galaxy properties will likely either resolve this tension in favor of baryonic feedback effects within the cold dark matter framework, or will push the modifications required into territory that clearly demands new dark matter physics. Either outcome would represent genuine progress, narrowing the range of possibilities and bringing the true nature of dark matter into sharper focus. One of the more profound implications of the dark matter story, often overlooked in technical discussions of detectors and candidates, is that dark matter was essential to the existence of life. The universe as we see it today, with its galaxies, its stars, its planets, and its oceans and atmospheres, where chemistry and biology operate, is not what the universe would have looked like without dark matter. The formation of large-scale structure in the universe, the process by which the nearly smooth early universe became the complex, hierarchical web of filaments and voids and clusters that we inhabit, required dark matter as the gravitational seed. In the very early universe, ordinary matter was too strongly coupled to radiation to clump effectively. The pressure of the photon baryon plasma resisted gravitational collapse, preventing ordinary matter from forming dense structures until the universe had cooled enough for atoms to form and the radiation pressure to drop. But dark matter, which does not interact with radiation, began clumping much earlier, forming potential wells into which ordinary matter could later fall once it decoupled from the radiation field. Without dark matter, the first stars would have formed much later, if they formed at all. The first galaxies would have taken longer to assemble, been smaller and less structured, and the chemical enrichment of the universe through stellar nucleosynthesis, the production of carbon, oxygen, nitrogen, and all the other elements necessary for chemistry and biology, would have proceeded more slowly or not proceeded at all in the forms required for life. The researchers who produced the Webb dark matter map noted this connection explicitly. Without dark matter, they observed, we might not have the elements in our galaxy that allowed life to appear. Dark matter is not something encountered in everyday life on Earth, or even in our solar system, but it has definitely influenced us. The carbon in your body, the oxygen in your lungs, the iron in your blood, are all traceable through the long chain of stellar evolution and galactic assembly to the gravitational influence of a substance you will never touch, never see, and never directly experience. This is one of the more unsettling facts in all of modern cosmology. You owe your existence to something you cannot detect, cannot name, and cannot fully explain. The dark matter halos that surrounded the earliest protogalaxies created the conditions for the first stars to form, and those stars forged the elements that would eventually find their way into living things. The invisible ghost that built everything is also the invisible ghost that built you. The connection between dark matter and life is not a metaphor. It is a chain of physical causation, documented at each step by observations and simulations, running from the quantum fluctuations of the inflationary epoch through billions of years of gravitational amplification to the formation of the solar system and the origin of life. Understanding dark matter better is, in a very literal sense, understanding the ultimate physical preconditions for your own existence. This perspective reframes what might otherwise seem like a purely abstract scientific puzzle. The dark matter problem is often presented as a question about exotic particles in remote corners of the universe, a problem for specialists with equations that most people will never encounter. But the stakes of the problem are as immediate and as personal as any question in science. Because the answer determines what kind of universe we live in, and how we came to be in it. The invisible majority of the universe shaped every structure that exists, drove the formation of every star and galaxy, and created the conditions for the chemistry that eventually produced you. Understanding what it is, and why it has the properties it has, is understanding the most fundamental context of human existence. Cold dark matter, in its simplest form, treats dark matter particles as entirely self-inert, passing through each other without interaction just as they pass through ordinary matter. This simplicity was one of the model's attractions, because it meant that dark matter behavior could be calculated with purely gravitational physics, without the complications of additional forces. But a growing body of observational evidence, and recent theoretical work published in early 2026, suggests that dark matter may not be entirely self-inert after all. Self-interacting dark matter, abbreviated as SITM, proposes that dark matter particles can collide with each other, exchanging momentum and energy in a way that modifies the structure of dark matter halos. The motivation for SITM comes from the same small-scale tensions that motivate fuzzy dark matter. If dark matter particles can scatter off each other within dense halos, the energy transfer between particles would smooth out the cusps of density that cold dark matter predicts, converting them into the observed cores. It would also reduce the number of dense substructures within galactic halos, potentially explaining why so few of the predicted satellite galaxies are observed around the Milky Way. And it would modify the structure of dark matter halos in galaxy clusters in ways that have been tentatively detected in observational data. Simulations published in January 2026 model the form of self-interacting dark matter in which the cross-section for self-interaction is velocity-dependent, large at low relative velocities within dwarf galaxies and smaller at higher velocities within galaxy clusters. This velocity dependence is motivated by the analogy with ordinary nuclear physics, where interaction cross-sections are also velocity-dependent, and it provides a way to reconcile the different small-scale structure observations at different scales. The results showed that velocity-dependent self-interacting dark matter could simultaneously resolve the cusp-core discrepancy in dwarf galaxies and be consistent with the constraints from galaxy cluster observations, providing a more complete solution to the small-scale structure problems than constant cross-section models. The critical next step is to identify observable signatures of self-interacting dark matter that distinguish it from cold dark matter in a way that current or near-future surveys can detect. Several such signatures have been proposed, including specific patterns in the shapes of dark matter halos inferred from gravitational lensing, characteristic features in the distribution of satellite galaxies, and distinctive behaviors in the merging of galaxy clusters where dark matter substructures might be expected to show interaction effects. The Vera Rubin Observatory, processing the largest galaxy survey ever conducted, and the Euclid mission, mapping the three-dimensional distribution of galaxies across large volumes, are expected to provide data relevant to distinguishing these models within the next several years. The self-interacting dark matter framework also has implications for the search strategy in direct detection experiments. If dark matter particles can interact with each other, the cross-section they present to ordinary matter may be related to their self-interaction cross-section through the same mediating particle, and constraints from the self-interaction side can inform predictions for the direct detection side. The connections between the astrophysical observations of dark matter structure and the particle physics searches for dark matter in detectors are becoming more intimate as both fields mature, and the synthesis of these two lines of evidence is one of the most promising developments in the broader dark matter research program. Dark matter's self-interaction, if real, would mean that the dark sector is not simply a population of inert gravitational sources, but a more dynamic entity with its own internal physics, capable of redistributing mass within halos over time in response to collisions between its own constituent particles. This would make the dark matter halos of galaxies and clusters living, evolving structures, responding to their own internal dynamics, as well as to the external gravitational environment, and the observational signatures of that evolution are now being actively sought in survey data from the largest telescopes ever trained on the sky. The physical experience of working at a deep underground dark matter detector is worth pausing on, because it offers a window into the kind of science that the dark matter problem demands, science conducted in conditions chosen specifically to create the quietest, most radiation-free environment achievable on Earth. SNOLAB in Sudbury, Canada sits 2 kilometers below the surface in an active nickel mine, accessed by a cage lift that descends for nearly 10 minutes through rock that has been in place since the Precambrian era, more than 2 billion years old. At that depth, the cosmic ray muon flux is reduced by a factor of approximately 50 million compared to the surface. The background of natural radioactivity from the rock walls is managed by a combination of shielding, pure water tanks, and scrupulous cleanliness protocols, including requirement that all personnel shower and change into specialized cleanroom suits before entering the detector area. The super CDMS detectors at SNOLAB are cooled to approximately 15 millikelvin, roughly 15 thousandths of a degree above absolute zero, using dilution refrigerators that can take weeks to reach operating temperature once they begin cooling from room temperature. At this temperature, the germanium and silicon crystals that form the detector elements become superconducting, and tiny phonon sensors etched onto their surfaces can detect the minute vibrations produced when a particle deposits even a small amount of energy in the crystal. The energy threshold for detection is measured in electron volts, far smaller than the energies involved in ordinary chemistry or radioactivity. The extreme sensitivity of these detectors means that every possible source of background signal must be carefully characterized. Natural radioactivity in the detector materials, including trace amounts of uranium and thorium present in even the purest laboratory-grade metals, contributes a baseline of events that must be subtracted. Neutrons produced by cosmic ray muons that still occasionally penetrate the 2-kilometer rock overburden mimic dark matter events and must be tagged and removed. The detector housing and cryogenic system are constructed from carefully selected low radioactivity materials that have been characterized for background contributions. The result of all this engineering is an instrument of extraordinary sensitivity, capable of detecting interactions that deposit energies thousands of times smaller than those from natural radioactivity, operating in an environment quieter than any naturally occurring place on Earth. And yet, after years of operation, the detectors have found no convincing dark matter signal. The silence is not failure. Each day of operation that produces no signal is a constraint, a statement that dark matter does not interact with these specific materials at the energies and cross-sections that would have been detected. The silence narrows the possibility space, pushing the search into regions where new detector technologies are required. The quiet of the underground laboratory is itself a kind of science, a methodical elimination of the possible, conducted in the deepest places accessible to human construction, in search of the particles that may make up most of everything. The scientists who work at these underground facilities describe the experience in terms that capture something of the peculiarity of the enterprise. You go deep underground into the oldest rock on Earth to listen for the rarest signals in the universe. And you do this surrounded by elaborate machines cooled to temperatures colder than deep space, in chambers shielded from every known source of background radiation, waiting for a particle that may or may not choose to announce itself. The work has a meditative quality, a combination of intense technical vigilance and the kind of patience that only a genuinely deep mystery can motivate. Most of the scientists who have spent careers on dark matter direct detection have not found what they were looking for. They have found instead the precise shape of what is not there, which is the form progress takes when the signal is this faint and the universe is this good at hiding what it is made of. Dark matter is often discussed alongside dark energy, and while the two are often mentioned together, they are distinct phenomena with different properties, different evidence, and different implications for the future of the universe. Dark energy is the name given to whatever is causing the expansion of the universe to accelerate. When astronomers in the late 1990s measured the distances and recession velocities of distant supernovae and found that the expansion of the universe was speeding up rather than slowing down as gravity would predict, they required a new ingredient in the cosmological model, something with negative pressure, something that acts against gravity on cosmological scales, something that accelerates the expansion of space itself. That ingredient was named dark energy, and it constitutes approximately 68% of the total mass energy of the universe, compared to dark matter's approximately 27% and ordinary matter's 5%. Dark energy differs from dark matter in a fundamental way. While dark matter clumps under gravity and is responsible for the formation of all cosmic structure, dark energy is smooth, distributed uniformly through space, and is responsible for the accelerating expansion that will eventually pull all large-scale structures apart. Dark matter and dark energy are in some sense in opposition. Dark matter pulling things together, dark energy pushing them apart, and the ultimate fate of cosmic structure depends on the balance between them. The nature of dark energy is even less understood than the nature of dark matter. The simplest explanation is that it is a property of space itself, a cosmological constant that Einstein originally introduced and then abandoned, the energy of the quantum vacuum pervading all of space-time. This explanation has the virtue of simplicity, but the challenge of requiring that the vacuum energy have exactly the right value to match observations, a value that quantum field theory predicts should be different by many orders of magnitude. The discrepancy between the predicted and observed vacuum energy density is one of the most embarrassing problems in theoretical physics. Alternative explanations for dark energy invoke scalar fields, called quintessence, that vary in space and time, or modifications to general relativity at cosmological scales, or other exotic physics. These alternatives make different predictions for the evolution of the universe's expansion rate over time, and measuring that evolution precisely enough to distinguish between them is one of the primary scientific goals of missions like Euclid and the Nancy Grace Roman Space Telescope. Understanding dark matter and dark energy together, their properties, their origins, and their relationship to each other and to ordinary matter, is the central challenge of modern cosmology and the next decade of observations. From Webb, from Rubin, from Euclid, and from ground-based surveys, will produce data bearing on both in quantities that dwarf anything available today. The distinction between dark matter and dark energy is worth holding clearly in mind because they are sometimes conflated in popular discussion. Dark matter is matter, in the sense that it has mass, exerts gravity, and clumps into structures. Dark energy is not matter but something more like a property of space itself, a pressure that acts against gravity at the largest scales. Dark matter made the universe more structured over time, pulling matter together into the hierarchies of galaxies, clusters, and superclusters that we observe. Dark energy is making the universe less structured, pushing distant structures apart and eventually driving them beyond the horizon of detectability. Both are invisible, both are poorly understood, and both are essential to explaining the universe we actually observe. But they are different mysteries, calling for different explanations and different experimental approaches, and conflating them risks obscuring the specific challenges each presents. The cosmic web is the largest structure in the universe, and it is primarily a dark matter structure, with ordinary matter playing a secondary, tracing role. The cosmic web consists of filaments, sheets, and nodes of dark matter, separated by vast empty regions called voids, all on scales of hundreds of millions to billions of light years. The nodes, where multiple filaments intersect, are the sites of the largest galaxy clusters, dense concentrations of thousands of galaxies embedded in massive dark matter halos. The filaments connecting the nodes are strands of dark matter along which gas flows, feeding the clusters at the nodes with material that becomes stars and galaxies. The voids are regions from which dark matter and gas have been drawn outward by gravity, leaving nearly empty regions that contain only the most isolated galaxies. The formation of the cosmic web is one of the major successes of the cold dark matter model. Beginning from the nearly smooth initial conditions of the early universe, with only the tiny quantum fluctuations of inflation as seeds, gravitational amplification over billions of years produces a web whose statistical properties match those observed in galaxy surveys with remarkable precision. The cold dark matter model predicts the right amount of structure on the right scales in the right pattern, confirming that its basic premise, slow-moving dark matter clumping under gravity, captures something essential about how the universe's skeleton was built. The Webb Dark Matter Map published in January 2026 provided the most direct visualization of the cosmic web's dark matter component ever produced, showing the filamentary structure of dark matter as it interlaces with the visible galaxy distribution across a wide field of sky. The 800,000 galaxies visible in the map are the luminous tracers of an underlying dark structure that outweighs them by a factor of 5 to 1. And the blue overlay showing the dark matter distribution is a map of the invisible majority that has been shaping the visible universe since the first stars formed. The cosmic web is not static but is still evolving, with the densest nodes continuing to grow by accreting material from the surrounding filaments and the voids continuing to empty. The dark matter halos around the most massive galaxy clusters are among the most dynamic structures in the contemporary universe, growing at measurable rates that can be tracked by monitoring the velocity fields of infalling galaxies and the temperature distribution of the hot gas within the clusters. Within this web, the Milky Way sits in a relatively ordinary location, embedded in a filament connected to the Virgo cluster and flowing, as the Great Attractor episode explored, toward the gravitational center of the Laniakea supercluster. The dark matter halo surrounding the Milky Way extends well beyond the visible disk of the galaxy, probably out to several 100,000 light years, and within that halo the dark matter density is much higher than in the cosmic average, making the galactic center region one of the more promising places to search for signals of dark matter annihilation, which is exactly what Totani's gamma-ray analysis has been probing. The recognition that we live inside a dark matter halo, immersed in a concentration of invisible matter that extends far beyond the stars we can see, changes the picture of what our galaxy is in a fundamental way. The Milky Way that appears in our skies, the band of stars arching across a dark night, is the luminous component of a much larger dark structure. The visible galaxy is the candle flame. The dark halo is the vast invisible space around it, extending into the intergalactic medium, connecting through filaments to neighboring halos, part of the continuous web of dark matter that structures everything at scales larger than a galaxy. The cosmic web is not something that exists out there, in the distant universe, visible only through telescopes. It is the structure we are embedded in, and the dark matter that forms its skeleton is present here, now, in the space around you. The detection of dark matter, if and when it occurs, will be one of the most significant scientific events in the history of physics, and thinking about what it would mean helps to convey the importance of the search currently underway. A confirmed dark matter detection, whether from a direct detection experiment finding the signature of a dark matter particle collision in an underground detector, or from an astronomical observation showing the unambiguous signal of dark matter annihilation in gamma rays, or from a particle accelerator producing dark matter particles in a high-energy collision, would first of all confirm that dark matter is real in a different and more direct way than the gravitational evidence. Gravitational evidence is compelling but indirect. A particle-level signal would be the first time that a dark matter particle had been directly registered by a human instrument. The first time that 27% of the universe had sent a message that we could actually read. More importantly, a detection would reveal the properties of the dark matter particle, its mass, its interaction cross-section with ordinary matter, and depending on the detection channel, additional properties like its annihilation products, its spin, or its coupling to other forces. These properties would constrain the theoretical models in a decisive way, eliminating candidates that do not fit and potentially pointing toward the class of extensions of the standard model that is actually realized in nature. Detection would also open entirely new lines of inquiry. If dark matter has a non-zero interaction cross-section with ordinary matter, even a very small one, then it might be possible to study that interaction in detail, to build instruments that can characterize the dark matter distribution in the solar neighborhood with precision, to learn about the dark matter halo of the Milky Way from the inside, and to use dark matter as a probe of extreme astrophysical environments that are otherwise inaccessible. The possibility that dark matter might interact with other dark particles, forming a dark sector with its own forces and structure, is particularly intriguing. If there is a dark photon, an analog of the ordinary photon that mediates an electromagnetic-like force between dark matter particles, then the dark sector might have its own chemistry and dynamics. Not as rich as ordinary matter chemistry, because dark matter does not form complex structures at small scales, but real and potentially detectable through its effects on the large-scale structure of dark matter halos. A detection would not end the mystery of dark matter. It would transform it from a mystery about existence into a mystery about properties, from the question of whether dark matter is real into the question of what kind of real thing it is, and that second question would open decades of further research, further experiments, and further theoretical development. The end of the dark matter problem, properly understood, is not a moment but a transition from a science of inference to a science of characterization, and the first detection would be the beginning of that transition. The history of science is full of moments when a previously invisible phenomenon was detected for the first time, and each such moment opened a new field of inquiry rather than closing an old one. The first detection of X-rays opened medical imaging. The first detection of radio waves opened radio astronomy. The first detection of gravitational waves opened an entirely new observational window on the universe. A dark matter detection would be of this character. Not an endpoint but a beginning, the moment when the universe's hidden majority finally agreed to be measured, rather than merely inferred. Everything that follows from that moment, all the characterization and the theoretical synthesis, and the experimental refinement, would be built on the foundation of that first decisive signal. The moment when a particle that makes up most of the universe knocked once, faintly but unmistakably, on the instruments that humanity built to listen for it. As you lie in the dark tonight, the dark matter halo of the Milky Way is passing through you. Not metaphorically. Dark matter particles, according to the best current estimates, are present in the solar neighborhood at a density of roughly a few 100 million particles per cubic meter, streaming through the Earth at velocities of around 200 to 300 kilometers per second relative to the galaxy's rotation. At any given moment, a large number of them are passing through your body, through the walls of the room you are in, through the planet itself, without leaving any trace, without depositing any energy, without interacting with any of the atoms they are threading through. One of them, perhaps once in your lifetime, if the cross-sections are in the right range, will collide with a nucleus in a detector somewhere in the world. The energy deposited will be equivalent to a few atoms vibrating slightly more than they were a moment before. The detector will register a signal. The analysis pipeline will flag it for review, and somewhere, a scientist will look at the data and begin the careful work of determining whether this is noise, background, or something else entirely. This is the kind of patience that dark matter science requires, and it is a virtue that the universe has been exercising for 14 billion years, while the dark matter halos drifted through the growing cosmic web, patient and invisible and absolutely essential to everything that happened in the universe after the first 100 million years. The dark matter problem is also a problem about human knowledge and its limits. We have known for nearly a century that most of the universe is made of something we cannot identify. We have built the most sensitive instruments in history to find it, buried them 2 kilometers underground, cooled them to within thousandths of a degree of absolute zero, and watched them for years. We have mapped its distribution across 800,000 galaxies using the sharpest telescope ever pointed at the sky. We have detected a possible gamma-ray signal from its annihilation at the center of our galaxy. We have found hints that it may be fuzzier, more quantum, more interactive with neutrinos than our standard models assumed. And we do not yet know what it is. This is not an embarrassment. It is a testament to how genuinely strange and genuinely deep the universe is, that the dominant form of matter can hide from every instrument designed to detect it for nearly 100 years of dedicated searching. The dark matter is patient. The science chasing it has to be equally patient and equally determined. The patience required is not passive. It is the patience of someone who has committed to understanding something that will not reveal itself easily, who keeps building better instruments, refining better models, and asking better questions, knowing that each improvement brings the answer a step closer, even when no signal appears. The scientists who have spent careers on dark matter without finding a particle to point to have not wasted their work. They have mapped the shape of the mystery with unprecedented precision, and that shape is information, telling us where the answer must not be, and therefore narrowing the space where it must lie. And right now, in 2026, that space is narrowing faster than at any previous moment. The Webb telescope has mapped the dark matter distribution across 800,000 galaxies. The Super CDMS detector has reached operating temperature underground in Canada. A possible gamma-ray signal from dark matter annihilation is being evaluated by independent teams. A hint of dark matter interacting with neutrinos is being tested by the largest sky surveys in history. The Roman Space Telescope will launch later this year and map dark matter across an area thousands of times larger than anything Webb can cover. The answer may not arrive this year or this decade, but the field has never been closer. The instruments have never been sharper, and the questions have never been more precisely posed. Sleep well. The dark universe is moving through you right now, and in laboratories underneath mountains and deserts and ancient rock. Instruments are listening for the moment it finally agrees to speak.